Hello, welcome to this lesson of the Linear Algebra Tutor. In the last section, we were introduced to inconsistent systems. Those are systems of equations that don't have a solution. There's no common point that's going to satisfy all of those equations in that last case that we had. Now what we're going to do is begin to talk about cases when we have an infinity of solutions. And this is the kind of stuff that even though you may have been exposed to it in an algebra class before, or in a previous class, we're going to be doing things a little bit differently in the context of linear algebra. So the way we're going to solve it and the way we're going to write our solution is going to be how you'll be expected to do it in a typical linear algebra class. So first of all, let's just write a system of equations down. It's not going to look too special at first. So we'll have x plus 2y minus z is equal to 1. Then we'll have x plus z is equal to 3, and x plus y is equal to 2. Now you would never know by looking at this. There's no way that you can know by looking at this. But this set of equations actually has an infinity of solutions, an infinite set of points. It doesn't mean any point in space is a solution. It just means that there exists a set of points, an infinity of those such points, that will actually satisfy the set of equations. So what we're going to do is go ahead and solve the problem using matrices, and then I'll kind of draw something on the board to illustrate how you can have an infinite set of solutions to a system like this. But first, let's just jump into the math and see what the matrix algebra stuff is telling you, the linear algebra stuff is telling you. You're not going to know until you get down to the end if this is a consistent set of equations, an inconsistent set of equations, or if it contains an infinity of solutions. So let's go ahead and write it down. Here's our augmented matrix. We have 1, 2, negative 1, 1. All right, and then we have 1 for x, nothing for y in here, so we have to put a 0. We have a 1 for a z, and then we have a 3 over here. 1 for x, 1 for y, nothing for z, so we have to put a 0, and then we have a 2. So this is my augmented set of equations. All right, now I feel like we have done enough row reduction where you kind of know what to do. You would take this guy, multiply it by negative 1, add it to this, that would give me a 0 here. You would take this times negative 1, add it to this, that would give me a 0 here, and then you would continue on going. And what you're trying to do is you're trying to get the diagonal elements, all ones along the diagonals, and you want to get zeros everywhere else. That's what you're always trying to do. But what you're going to find is that if you have this set of equations where you have an infinity of solutions, that you're not going to be able to do it. You're not going to be able to do that. You'll try to do one thing and then do the next thing and do the next thing, but you'll end up figuring out eventually that there's no way to achieve a diagonal set of ones with an off-diagonal set of zeros for cases where it's an infinity of solutions like this. So instead of showing all of those steps, I feel like we have done enough row reduction now, where I'm just going to put a little arrow and I'm going to say row reduction. So after some row reduction, we arrive at the following thing. 1, 0, 1 with a 3. 0, 1, negative 1, negative 1, 0, 0, 0, 0. All right, so you might say, well, how did we get there? Well, you're applying the same rules. You can interchange rows, you can multiply a row by a scalar, you can add one row to another. But notice what we're still attempting to achieve what we can. We still have a 1 here, we still have a 1 here, but we were unable to get a 1 here, and that just falls out from when you do the actual row operations. You're going to find out that when you try to put a 0 here, when you try to multiply and get a 0 here, it ends up knocking this guy out to 0 too. So there's no way that you can actually get a 1 in this position without annihilating everything else. And that's why it ends up like this. So there's a few little row reduction steps, nothing different than what we have done before, and you arrive at this point. And I'll tell you right now, the big clue that this is an inconsistent, I'm sorry, not an inconsistent, the big clue that it is an infinite set of solutions here is the fact that we've done everything properly, but we get all zeros with a 0 over here. When you see that kind of pattern, when you see all of your variables go to 0 with a 0 on the other side, that almost always is going to mean that you have an infinity of solutions. So I'm trying to teach you a little bit of pattern matching. As you're doing your row reduction, if you get down to that point, you see all zeros across, including on the right-hand side of the dotted line of the matrix, then that's almost always going to mean that there's an infinity of solutions. Let me show you how that's the case. Let's say that this is what we got at, and we wanted to write down the solutions here. First of all, notice, you might say to yourself, well, Jason, why didn't you make this 0 and this 0? Because we're trying to get a diagonal elements. Why didn't you knock this out and this out? Well, I'll turn it around and ask you, how do you think we should do that? Given that we arrived from here to here, How do you think we should make this 0? Normally the way you do it is you multiply the third row by something and you add it. But since there's all zeros in the bottom row, there's no way that you can multiply this by something and add it to this one or add it to this one to get rid of these numbers. That's why there's still numbers here. I cannot eliminate them because that third row went to 0 when I attempted to do my row reduction. So that's why we're unable to get rid of these. That's why it doesn't quite look like a diagonal matrix. So at some point you have to stop and say, well, I cannot achieve a diagonal matrix. Let me write down the solution as I see it. All right? And so what I'm going to have then is I will say this is x, so it'll be x. This is nothing, so this is y and z. So x plus z is equal to 3. The second equation is y, which is the middle column, minus z is equal to -1. And the third guy, so this is telling me something about x, this is telling me something about y. The third one, I'm going to write it as 0 times z is equal to 0. 0 times z is equal to 0. So it looks similar to the last problem we did when it was inconsistent, but it's a little bit different. We have a 0 on this side. Let me ask you, what value of z can I stick in here and satisfy this equation? The answer is I can put any value of z in there that I want to. I could put z is equal to 1,000,000. I could put z is equal to -200. I could put z is equal to 4/5. If I stick a number here and multiply it by 0, I'm always going to get 0, no matter what value of z I put in there. That's why there's an infinite number of solutions to this, because no matter what value of z I pick, I'm guaranteed to satisfy this third equation. This is different than the last problem. The last problem we had something like 0 times some variables equal to 5. That's inconsistent because there's no value you can stick in there to satisfy. Here is exactly the opposite. Any value I put in is able to satisfy this guy. So we say that I can pick a value of z here, any value I want, and I can still satisfy the system of equations. So we say that the solution of the system is really dependent on whatever value of z I happen to pick. So we call this a dependent system. Dependent on what? Well, dependent on whatever value of z I pick. If I pick z is equal to 1, for instance, it satisfies the third equation. Then I can put a 1 in here and a 1 in here, and I can solve for x and y. So the value of x and y that I compute is dependent on whatever value of z I happen to choose. Let's say I put z is equal to 5. That certainly does satisfy this equation. So I put 5 here and I put 5 here, and I do the subtraction. I get a corresponding value of x and y. Let's say I put z is equal to 100 or 10 million or z is equal to pi or something. And then for each of those cases, I can stick that value of z in here and calculate a corresponding value of x and y. So that's how I told you at the beginning there's an infinite set of solutions. I pick any value of z I want, and I get a corresponding value of x and y that go along and fit into that solution space. All right? And before I go farther, let me just kind of try to illustrate how could you possibly visualize how this could be. I mean, in other words, I understand the math here, but why is it possible that you could have an infinite set of solutions like that? Well, look at our original equations. This is x, y, and z, so this is three-dimensional space. When you have linear equations like this in x, y, and z, generally they're representing a plane. You remember the equation of a plane in three-dimensional space is going to be coefficients in front of x, y, and z, and a number on the right-hand side. So each of those equations are just representing planes oriented different directions in three-dimensional space. So here's a plane, here's a plane, here's a plane, here's a plane, and so on. A flat structure we call a plane. Each of those equations is representing that. So in this particular case, I'm going to do my best to draw this. I'm not a great artist, so please don't shoot me. Now you have to use your imagination here because I'm not a great artist, especially in 3 dimensions, but this is a plane, so pretend you're looking at it edge on, right? So I'm going to draw this plane like this, edge on into the board, all right? Now let's say you have another plane cocked at 45 degrees like this, also edge on into the board. And let's say you have another plane cocked at 45 degrees this way, edge on into the board. So what you're looking at here is edge on, 3 planes, one like this, and one like this. Notice there's a common point in the center, so if these were just 3 lines, there would be simply one point that would be common to all 3 of these lines. But since this is a plane, and the planes extend in infinite directions this direction, and the one that's tilted here is infinite long in this direction, one tilted this way is infinite long in this direction, then really there is a line of points that extends along the plane in infinity in this way and infinity in this direction. And that line is common to all three planes because the planes are all intersecting there, and they're going on in the direction for infinity there. That's how you can have an infinite solution space like that. That's in one example. Now, if you have higher order equations, it's kind of harder to draw, but this is basically the idea here. This falls out from what we see at the bottom, that if we choose any z, it works out, and we can calculate corresponding values of x and y. So you have to be careful. When I tell you that there's a dependent solution here, or there's an infinity of solutions, it doesn't mean that every single point in the universe is a solution. I mean, the point out here is not a solution common to any of these planes. The point over here is not common, the point over here is not common, the point over here is not common. But the set of points that lies along the line that intersects all three of those planes is common to all three of those planes. And that line extends to infinity in both directions, so there is an infinite number of points that exist along that line that satisfy it. So in a basic algebra class or high school class or something, you might just get to this point and you might say, okay, it's a dependent system. There's an infinity of solutions dependent on the value of z I pick, and then you would be done. You would typically circle your work and say that you were done. But this is linear algebra. It's a little bit higher level. So what we're going to do then is write the solution a little bit more explicitly. Let me write these little equations down. X plus z is equal to 3. Or so say y minus z is equal to -1, and 0 times z is equal to 0. So these are the little equations that we got out of our system after we did the row reduction. And what we have said is that the third equation implies that z can be anything. Z can be anything. So the way you handle that in terms of writing a real solution down is you say that z can be anything. So we assign it a value of k. Z can be 5, z can be 10, z can be 14. We use the letter k like this to denote any number we want. We say that that is the case. Now then we go back up to our other equations and we say, all right, x plus z is equal to 3. All right? And we can rearrange that and we can say that x is equal to 3 minus z. Notice we just pull the z over there. And then because we know that z is equal to k, we can say that x is equal, let me write it underneath here, x is equal to 3 minus k. All right, so this is kind of important. This is kind of important. Let me switch colors. I'll draw like a little line in between here. Let's look at the third equation. Y minus z is equal to -1. What this means is if we solve for y is equal to -1 plus z. But we know what z is. It's just a constant. So we say y is equal to -1 plus k, like this. And that's an important relation. So you see, all we've done is we've said z can be any number we want. We call it k. And once we have that number locked down, we can calculate the corresponding value of x and y, much like we just said a minute ago in terms of words. And let me write z down here, right underneath it. So z is equal to k. So this is important. This is important. And I've rewritten this one down here, so that's important. I'll take the asterisk away here because I've just rewritten it down below. So essentially, we have a solution for x, a solution for y, and a solution for z. All that remains is that whatever, it's an infinite set of points along a line that satisfy what we have here. We pick whatever value we want for z, and then we get a corresponding value of x and y. Now in linear algebra, the way you write an infinite set of solutions like this is the following. Our solution we call capital X, that's a matrix, a column vector that describes everything. Let me write it down and then I'll describe it to you. So the number that we have for X is 3, the number that we have for Y is -1, the number that we have for 0, we don't really have anything except K, so we'll leave it as 0 right there. And then you write it as plus K times another column matrix. K times this would be -1. K times, to factor out there, would be +1, and this would be 1. Okay, this is how you would write your dependent solution down on a test in linear algebra class. In previous classes, when things are not quite as complicated, you would just say, hey, it's dependent, or it's an infinite solutions, whatever, I'm done. Here, you're going to be expected to write it down as a linear combination of two solutions. One of them is just a set of numbers. One of them is the part that depends on k, right? So notice how you read this. X y, and z, because the column vector here represents the x value, the y value, and the z value. So to find out what x is equal to, it's 3 plus k times negative 1, which is 3 minus k. That's what we had written down here. Then we have negative 1 plus k, negative 1 plus k for y. Then for z, we have a 0 there. We just have k times 1, which is k. This is how you typically write it. You write it as, when you get it all in this form and you solve for, you define one of the variables and lock it down as k, you solve for the other variables in terms of k, and then whatever numbers you have, you put them in a column vector, and then everything that depends on k, you put them in another column vector with the k in front. Because you know that when you have a scalar out in front, you can just multiply there. So you're reading rows off here. Here's the value of x, here's the solution for y, here's the solution for z. Make sure you understand this. It's not rocket science, but it's something that you'll be expected to do. We'll do another problem in the next section, basically giving you additional practice. So the bottom line is you start with a system of equations. You cannot get it into a diagonal matrix. When you have all zeros like this, all the way across, it almost always is going to be dependent system. So we just set that guy that can be anything to k, solve the other variables in terms of k, and then we write it as we have written it here. So this is a dependent system. Dependent on what? It's dependent on whatever value of k that we choose, which is the value of z. That's why it's called dependent system. So it's an infinity number of solutions along the line that is the intersection of those three planes. Make sure you understand this. Follow me on to the next lesson. We're going to do another problem where we have an infinite set of solutions, a dependent solution set in linear algebra.